A team of researchers made a batch of Maya plaster using a 1,000-year-old recipe, lime, water, and the bark of a specific tree that grows in the Yucatán, pressed it into a mold, let it cure, and then broke it on purpose. They introduced a controlled crack across the face of the sample, sealed it in a humidity chamber, and put it under a microscope. Over the next 6 weeks, they watched the crack close, not fill in from the outside, close from the inside, crystal by crystal. The broken face of the plaster generating new mineral growth that bridged the gap, progressively sealing the crack until 70% of the original crack volume had been filled by material the plaster produced itself. No patching, no additives. The plaster responded to being broken the way a living tissue responds to being cut. Then they ran the same test on a sample of modern cement. Same crack, same conditions, 6 weeks. Nothing. The crack was exactly as wide at the end as it was at the beginning. The Maya knew something about how to make plaster behave like a living material. They encoded that knowledge in a recipe involving a specific tree, and that knowledge was passed down, intact, through craft tradition for 1,000 years. Surviving the Spanish conquest, the destruction of the codices, the collapse of the cities, because a handful of artisans in Copan in the Yucatán never stopped making lime the way their grandfathers showed them. Scientists asked Grok AI to explain what is actually in the bark that makes the plaster do this. The answer they got back reorganized everything they thought they knew about what pre-Columbian civilizations understood about materials. Here's what the analysis found inside the bark. The Chukum tree, Haverdia albicans, is a native leguminous tree of the Yucatán Peninsula. Its bark contains concentrated gallic acid and condensed tannins, organic polysaccharide compounds that have a specific structural property. They bind to calcium ions. When Chukum bark extract is mixed into lime slurry, the polysaccharide compounds disperse through the curing matrix and bind to calcium at the nucleation sites where calcium carbonate crystals begin to form. They don't prevent crystal formation. They control it, guiding the geometry of crystal growth, spacing the crystals at intervals, and creating an organic scaffold threaded through the inorganic mineral matrix. The result is not lime plaster with an additive. The result is a composite material, organic and inorganic phases, interlocked at the molecular scale, whose fracture behavior is fundamentally different from pure lime. When the composite cracks, the organic network at the crack face remains intact and provides nucleation sites for new crystal growth from dissolved calcium in ambient moisture. The crack triggers the repair mechanism. The damage activates the response. Grok's identification of this mechanism was not the finding that unsettled the researchers. That is the mechanism. What unsettled them was what Grok said next. This is not a novel composite architecture. This is nacre. I'm Dr. James Mercer. Subscribe now and turn on notifications. What I'm about to walk you through is in the materials science literature, in the hands of craftsmen who are still alive, and in a molecular structure that should not exist in a 1,000-year-old plaster recipe from the jungle. Let's go back to the beginning. To understand what Grok found, you need to understand what Maya construction actually achieved and why it survived conditions that modern materials cannot. The Maya civilization at its height, roughly 250 to 900 AD, built cities across the lowland jungle regions of what is now Mexico, Guatemala, Belize, and Honduras. The defining characteristic of Maya monumental architecture is not the stone pyramids, which draw most attention, but the plaster. Every major Maya structure was finished in a thick coat of lime plaster, applied to exterior walls, temple surfaces, courtyards, and floors, then polished to a surface that contemporary Spanish observers compared to white marble. The jungle is the harshest environment on Earth for construction materials. Annual rainfall in the Maya lowlands averages 2 meters. Humidity stays above 80% for most of the year. Biological growth, mosses, lichens, tree roots, finds and exploits every crack in a surface within months. Chemical weathering from rainfall, which is slightly acidic, dissolves calcium carbonate continuously. Modern render applied to structures in the same conditions typically fails within 5 to 10 years. It cracks, delaminating from the substrate as the underlying material moves seasonally, and once cracked, the jungle finishes the job within a season. The Maya plaster services at Copan in Honduras, at Palenque in Chiapas, at Chichen Itza in the Yucatán have been exposed to those conditions for between 800 and 1200 years. They are not intact everywhere. Centuries of abandonment, root damage, and looting have taken their toll, but the sections that survive show a durability that modern conservation materials applied in the last century have not matched. Conservators working on Maya sites have noted that their modern interventions, modern lime mortars and renders applied to stabilize ancient structures, degrade faster than the ancient surfaces they are meant to protect. The Maya formula was not just a historical curiosity preserved by inertia, it was technically superior to what replaced it, and the reason it was superior was not understood by anyone until 2023. The addition of organic materials to lime plasters is not uniquely Maya. Medieval European mortars sometimes incorporated animal fat, egg white, or plant-based additives. Ancient Chinese builders used sticky rice, as discussed in the previous video. The general principle, organic additives can modify the behavior of mineral binders, was empirically discovered by multiple ancient cultures. What made the Maya case different, and what kept it from being taken seriously as a technical finding, was the question of whether the Maya knew what they were doing or had simply stumbled onto a combination that happened to work. In the framework that dominated pre-Columbian archaeology through most of the 20th century, ancient Mesoamerican builders were understood as highly skilled craftsmen working within an empirical tradition. They knew what worked because they had seen it work, but they did not understand why. They were practitioners, not engineers. The idea that a pre-Columbian culture might have empirically identified the functional mechanism of a composite material at a level of specificity that modern materials science was still trying to decode was not a hypothesis that the field entertained. This framing shaped what questions got asked and what got published. The organic additives in Maya plaster had been noted in the archaeological literature since at least the 1980s. They were described as ritual components. Lime processing was a sacred craft in Maya society, and the addition of plant materials was interpreted as ceremonially significant rather than technically functional. The sacred framing and the technical framing are not mutually exclusive, but the sacred framing dominated the literature and the technical framing was not investigated. The 2023 paper changed that. And Grok's synthesis of that paper's findings changed the frame of what the Maya actually understood. The research team's instruction to Grok: take the 2023 compositional analysis of Maya plaster samples from Copan, cross-reference the identified organic compounds against the known literature on biological and synthetic composite materials, and identify what class of material the Maya plaster most closely resembles in terms of its microstructure and fracture behavior. The finding came back in three parts. The identification: the polysaccharide compounds in Chukum bark extract, gallic acid, and condensed tannins bind to calcium ions and template calcium carbonate crystal nucleation in a way that creates a specific microstructural architecture, alternating layers of organic and inorganic material at the nanoscale, with the organic network constraining crystal size and orientation while providing a continuous phase that spans the composite. This architecture is the defining characteristic of nacre, the material that lines the interior of mollusk shells and that we call mother of pearl. Nacre is calcium carbonate, the same mineral as chalk and limestone, organized by an organic protein scaffold into a composite that is 3,000 times tougher than pure calcium carbonate. The organic proteins account for approximately 1% of nacre's volume. They produce a 3,000-fold increase in toughness by controlling how cracks propagate. Instead of running straight through the brittle mineral, cracks deflect along the organic layers, requiring vastly more energy to propagate and arresting spontaneously at organic interfaces. Maya plaster uses the same architecture. not approximately the same principle. Organic scaffold templating inorganic crystal growth into a layered composite, operating at the same scale, producing the same crack arrest mechanism, the crack repair, the self-healing behavior, the 70% crack closure over 6 weeks observed in the experimental samples is produced by the same mechanism. The organic network at the crack face remains intact after fracture and provides nucleation sites that attract dissolved calcium from ambient moisture. New crystals nucleate on the organic scaffold and grow into the crack space, progressively bridging it. This is functionally identical to how bone repairs itself. The organic collagen scaffold in bone tissue provides the template for new mineral deposition at fracture sites. Maya plaster heals like bone. It is structured like nacre. Both of these are biological mineralization principles that modern materials science has been attempting to replicate synthetically for 50 years at the cost of hundreds of millions of dollars in research investment with limited success. The Maya were doing it with tree bark for 1,000 years. The craftsmen. Grok's analysis of the ethnobotanical literature flagged a finding that the research team had not connected to the chemistry. In the Copan region of Honduras and in parts of the Yucatán, there are still lime-working artisans who prepare plaster using Chukum bark extract, not because they know the molecular mechanism, because their grandfathers did it this way. The oral transmission of the recipe has persisted for at least 3 generations past the collapse of the cities that used the plaster at monumental scale. When researchers collected samples from these modern craftsmen and analyzed them, the compositions matched the ancient samples within normal variation. The recipe was never lost. The understanding of why it worked was never transmitted. The recipe survived because someone 1,000 years ago found the right trees through empirical observation and encoded the result in a craft tradition specific enough to survive everything that happened to the Maya civilization afterward. As the team continued the analysis, 3 additional findings emerged. The first revelation: the Maya knew which trees, in what proportion, at what time of year. Chukum bark is not the only organic component in Maya plaster at all sites. Analysis of plaster samples from different sites and different periods shows variation in the organic fraction. Different sites use different combinations of chukum with a second tree called giote or copal blanco, Bursera cimaruba, whose resinous bark contributes hydrophobic compounds that make the cured plaster water-resistant. The proportions vary by application. Exterior surfaces exposed to rain show higher giote content. Interior polished surfaces show higher chukum content. Different performance requirements, different organic formulations. This is not a single recipe passed down unchanged. This is a system of formulation. The same understanding applied differently based on the functional requirement of the specific surface. That is not craft repetition. That is applied chemistry, the knowledge that different proportions of organic scaffold compound produce different mechanical and water resistance properties in the cured composite, and the ability to adjust the formula to the application. The craftsmen who still make lime plaster in Copan do not know this, and they know one ratio, the one their grandfathers taught them, and they use it for everything. The systematic formulation knowledge, the understanding that proportions can be varied for different applications, was lost with the engineers who held it. The recipe survived. The engineering knowledge beneath it did not, in the same pattern observed with Roman concrete, where Vitruvius documented the formula and the understanding of why it worked was severed from the documentation. The second revelation, the Popol Vuh contains it. The Popol Vuh, the Quiche Maya creation narrative, recorded in writing in the 16th century, but preserving oral tradition of much greater antiquity, describes creation using a specific vocabulary of crystallization and becoming solid. The processes by which things become permanent in the Popol Vuh are described using language that, when analyzed against the Maya craft vocabulary documented by colonial-era Spanish priests, corresponds to lime processing operations, the sacred language of creation and the technical language of plaster making share the same root terms in the Kaichi vocabulary, this is not metaphor running in one direction, sacred language borrowing from craft language for poetic effect. The borrowing went the other way. Maya craft practice encoded the fundamental creative process of the universe as understood in Maya cosmology. Making lime plaster was not like creation. Making lime plaster was doing what creation does, taking fluid, unformed material and giving it permanent structure through a process that involves organic life. The trees were not an ingredient. They were the mechanism by which life was introduced into the mineral, doing what life always does, imposing order on inorganic matter. The Maya understood at the level of cosmology that their plaster worked because it was alive. The third revelation. Modern materials science has not synthesized nacre at commercial scale after 50 years of trying. The organic proteins that template nacre crystal growth, silk fibroin and chitin-based compounds are expensive to produce, difficult to incorporate into building materials at scale, and sensitive to the curing conditions that lime plasters require. The synthetic nacre that exists in laboratory settings is produced in controlled environments at costs that make it viable for specialty aerospace and biomedical applications, not for construction. Chukum bark is a tree. It grows in the Yucatán. Its bark can be harvested seasonally and processed by hand using techniques that require no specialized equipment. The functional analog of the most expensive composite material in modern aerospace manufacturing grows wild in the Mexican jungle, and the method of incorporating it into a building material has been transmitted in unbroken oral tradition to craftsmen who are alive today. The nacre principle, organic scaffold, templating inorganic crystal growth into a layered composite, does not appear only in mollusk shells and Maya plaster. Bone is built on the same principle. Collagen provides the organic scaffold. Hydroxyapatite, a calcium phosphate mineral, nucleates on the collagen fibers and grows in controlled orientation, producing a composite that is simultaneously rigid and impact-resistant and self-repairing. The collagen hydroxyapatite architecture of bone has been studied intensively for biomedical applications. Synthetic bone materials used in orthopedic implants and bone grafts attempt to replicate the organic-inorganic composite architecture of natural bone with mixed results. Sea urchin spines use a variation of the same principle. Coral uses it. The inner layer of eggshell uses it. The nacre principle is not a biological novelty. It is the standard solution that biological mineralization has converged on repeatedly across different organisms and different mineral systems because it is the solution that produces the best mechanical properties from the available ingredients. When Grok cross-referenced the organic compounds in Chukum bark against the organic compounds in biological mineralization systems, nacre proteins, bone collagen, sea urchin spine matrix proteins, it found that the polysaccharide profile of Chukum bark extract is not just functionally similar to nacre templating proteins. The molecular geometry of the tannin compounds in Chukum bark, the specific spatial arrangement of hydroxyl groups that bind to calcium ions, is structurally analogous to the calcium binding regions of the silk fibroin proteins that template nacre crystal growth in mollusks. Not the same molecule, the same binding geometry, different molecular structure, identical functional architecture at the calcium binding site. Modern computational chemistry calls this convergent molecular function. Different molecules arriving at the same three-dimensional solution to the same binding problem. It happens in drug discovery, different compounds that bind the same receptor by arriving at the same spatial configuration of interaction groups. It is well documented in synthetic chemistry. What is not well documented is a pre-Columbian population identifying a plant compound with the same calcium binding geometry as a marine protein scaffold and incorporating it into a building material with the same composite architecture as the shell of a mollusk. Here is what the academic response to the 2023 paper has not included: a re-examination of Maya construction through the lens of materials science rather than archaeology. The 2023 paper identified the organic compounds, characterized their effect on the crystal microstructure, and demonstrated the self-healing behavior in fresh samples. It was published. It was covered in science journalism. It was absorbed into the literature as an interesting finding about pre-Columbian construction practices. The framing that did not appear in the published paper and has not appeared in any subsequent publication is the one that Grok's synthesis produced, that Maya builders had empirically identified and encoded a biological mineralization principle that modern materials science has been attempting to replicate for 50 years. That framing has consequences. It requires acknowledging that pre-Columbian Mesoamerican builders possessed empirical knowledge of biomineral chemistry at a level of specificity that the conventional understanding of indigenous technical knowledge does not accommodate. The conventional understanding is that ancient builders worked by trial and error within inherited tradition. They knew what worked, but not why. The nacre principle finding implies something different. Not that the Maya understood molecular chemistry, but that they identified the correct biological system, the right tree with the right compound in the right concentration, through a process of empirical investigation sophisticated enough to distinguish between trees that are superficially similar and trees that have the right compound profile. The Yucatán has many leguminous trees with bark tannins. Chukum produces the tannin profile that works. Identifying Chukum specifically, as opposed to other available trees, required either extended systematic empirical testing, which implies an organized research capacity, or direct knowledge of the binding mechanism, which implies a level of understanding we have not attributed to pre-Columbian science. The 2023 paper did not raise this question. Grok raised it, and the team that asked the question has not yet decided how to publish the answer. So here is where this lands. Maya lime plaster made with Chukum bark extract is a biological mineralization composite, a material structured like nacre and functionally similar to bone, whose crack repair mechanism was demonstrated in controlled laboratory testing to seal 70% of introduced crack volume within 6 weeks without any intervention. Modern cement shows no comparable behavior. The organic compound responsible is a polysaccharide tannin from a tree that grows throughout the Yucatán and whose bark processing method has been transmitted in unbroken oral tradition to craftsmen who are alive today. Grok's analysis identified the mechanism, identified the nacre structural analogy, and identified that the molecular geometry of the Chukum tannin's calcium binding site is structurally analogous to the calcium binding regions of the marine proteins that template nacre crystal growth. Not functionally similar, structurally analogous, the same three-dimensional arrangement of interaction groups arriving at the same solution to the same problem in a tree and in a mollusk shell. The Maya creation text, the Popol Vuh, uses lime processing vocabulary to describe the act of creation itself. The craftsmen who still make Chukum lime describe the bark extract preparation using functional criteria, color, viscosity, readiness, that correspond to the optimal tannin concentration for crystal templating. They do not know why those criteria matter. They know the criteria. Someone, 1,000 years ago, identified the right tree in a jungle full of trees, determined the right preparation method, found the right concentration, understood that the formula varied by application, and encoded all of it in a craft tradition specific enough to survive the collapse of the civilization that produced it. When Grok was asked how a pre-Columbian culture might have identified Chukum specifically, not by trial and error across all available trees, but by targeting the tree with the right compound, the AI cross-referenced the compound profile of Chukum bark against every documented traditional use of the tree in Maya botanical records. Chukum appears in Maya ethnobotanical records not only as a construction material, but as a medicinal plant used specifically for, and this is the part the team was not expecting, the treatment of bone fractures. The same tree, the same compound used in Maya medicine to accelerate bone healing, used in Maya construction to make plaster that heals its own cracks. A compound that templates calcium crystal regrowth in living bone was used by the same culture in the same period to template calcium crystal regrowth in a mineral building material. That is not coincidence. That is the application of an observed principle across two domains. Someone looked at a healing bone, identified that the tree was involved in the process, and asked, what else could this do? The craftsmen who still use Chukum for lime don't know about the bone medicine. The healers who still use Chukum for fractures don't know about the plaster. The knowledge split along the lines of the craft traditions that survived, but it was once held by people who understood both because they understood the principle. Subscribe now and turn on notifications. When the next piece goes up, you need to have seen this one first. I'm Dr. James Mercer. The moment I have more, you'll be the first to know.